In today's lesson, we are going to be looking at uniform distributions. So in this lesson and in the future lessons for this unit, they are going to be similar in style. We're going to be looking at different scenarios or different types of probability distributions. In those lessons, we're going to be still doing the same types of things. We're going to be creating a probability distribution table where we look at all the different outcomes and how to find the probability of each of those outcomes. And we're going to look at finding the expected value of these scenarios. We're also going to be looking at creating a probability distribution graph, and we're going to incorporate using technology to find or to help us create these things as well. So the main difference is just going to be the type of scenario we look at, which will then inform us on what type of formulas we should be using. So the first one is uniform distribution. And a uniform distribution or uniform distributions occur when all the outcomes are equally likely. So if we have a scenario where all outcomes are equally likely or they have an equal probability of occurring, it's considered a uniform distribution. So for all outcomes x, we can calculate the probability by doing 1 over n, where n is the number of outcomes. So our simplest type of probability. So for some examples, tossing one die, a regular 6-sided die, I would say I have a 1 in 6 chance, or each outcome has a 1 in 6 chance of occurring. For tossing a coin, a 1 in 2 chance, heads or tails, 50%, 50-50. A spinner with 4 equal parts, a 1 in 4 chance. So each outcome or each part has a 1 in 4 chance of occurring. So they're all equally likely. So if I look at my first example, a wheel is divided into equal sectors. Calculate the probability distribution of the spin outcome. So I'm going to look at x, or my outcomes. I have 0, 5, 10, 15, 20, and 30. What is the probability of each outcome occurring? Well, looking at my spinner here, each spinner has the same number, or each outcome has the same number of spaces, and each space is the same size and shape. So they're all equally likely. So in this case, 1 out of 6, because there's 6 spots, and one of them has 5, 0, one of them has 10, and so on. And they're all the same. So they all have a 1 in 6 chance of occurring. So probability distribution table, very easy to create for this type of scenario. To sketch the graph of the distribution, this is also just as easy. Keeping in mind our y-axis is going to be the probability, our x-axis is going to be our outcomes. We have then 0, 5, 10, 15, 20, and 30 for our spin amount. Our probability of x. So in this case, in terms of our scale, it doesn't really matter too much because it's all going to be the same. Right? 0 was 1 out of 6. To get a 5 was also 1 out of 6. I'm just going to alternate colors just to make it a little bit easier to see these bars. So there is our graph of our distribution. Now, what is unique about this shape? Or what do we notice about the shape? Right, some things that we should notice. One, it forms a box or a rectangle. Right, if I were to draw kind of a shape around it, I get this kind of box or rectangle shape around it. You could also say they are all the same height. And you could also say they're evenly distributed. So that's the nice thing about uniform distributions. Any type of uniform distribution should have these same characteristics when we graph it. because all the probabilities are going to be the same. For C, calculate the expected value of the spin outcome. So I want to know, if I spin it, what is the expected value? Or you could think about weighted average. What is the average of my spin? So going back to the previous lesson, we do have this formula. Expected value, the expected value is the sum, I can draw or write, sigma, or sum of x times the probability of x occurring. So I'm going to go through and list all my outcomes. So 0 times the probability of occurring 1 out of 6, plus, for the sum, the next outcome, 1 times 1 out of 6, or sorry, not 1, 5. Plus the next one, 10 times 1 out of 6, plus 15 times 1 out of 6, plus 20 times 1 out of 6, plus 30 times 1 out of 6. I can simplify this instead of having to go through and multiply and add, and so on. I see that I'm multiplying by the same number, 1 out of 6. So I can go through and take that common factor out and basically just add up all my numbers first, and then multiply by 1 out of 6. And this basically works out to 80 over 6, and this is essentially just the average. So we talked about in previous lessons, this formula actually gives us the weighted average, but when we're dealing with a uniform distribution, because all outcomes are equally likely, essentially I am just finding the average. So 80 divided by 6, 13.3. So therefore, the average value of each spin is 1330, or 13.3. Or you could round it to 13 if you wanted. For D, suppose you win the amount that the spinner lands on, and you must pay $15 to play. Is this considered a fair game? Explain. So a couple things we want to take into consideration here. We want to know if it's a fair game, and we must pay $15 to spin. So how do we consider it a fair game, or what do we need to find out if it's a fair game? And if it's a fair game, or what we need to do first, if we want to find out basically our net winnings. So I want to find out, in the end, taking into account what I pay, taking into account what I'm expecting to win, what is my net winnings, or my net gain? So here what we're going to do, we're going to take the expected value and subtract what we pay. So in this case, I'm expected to win 13.3, or you could say $13.30, but I have to pay $15 to play. So in the end, my net winnings are negative 1.7. So is this considered a fair game? No, it's not. Why? You lose, on average, $1.70 each spin. So it's not considered a fair game because you're going to be losing every time you spin. If it's a fair game, then it would equal out. What you pay is equal to what you're expected to win. Looking at another example of a uniform distribution, consider the number rolled when rolling a single die. And I want to again go through the same steps. Create a probability distribution table, find the probability of each outcome, create a graph, and find the expected value. So the probability, or each outcome, sorry. First we have 1, 2, 3, 4, 5, or 6. Those are all the outcomes when I roll a die. The probability of each is going to be the same, 1 out of 6. There's only one face with each number, and there are 6 of them. So similar to our last one, it's 1 out of 6. To construct my probability distribution graph, it's the exact same thing. Probability of x outcome, let's call it a roll amount this time. We have 1, 2, 3, 4, 5, and 6. Again, scale doesn't really matter because it's all the same for each outcome. 1 out of 6. 1 out of 6. 1 out of 6. 1 out of 6. And 1 out of 6. So exact same shape. Yes, it's the exact same probability, but not taking that into account, it's the exact same shape, regardless of what type of uniform distribution example I gave you. It should still have the same shape. So if I turn this into a game where you won the dollar amount of each roll, how much would you have to charge per roll to make it a fair game? So again, the key thing is a fair game. And in order to find out how much I would have to charge, I need to find out what is the expected value, or how much am I expected to win every time I roll. So again, the expected value is the sum of x times the probability of x, but we've talked about, because it's a uniform distribution, instead of going through and finding the sum of every single one multiplied by the probability, I can just find the average. So 1 plus 2 plus 3 plus 4 plus 5 plus 6. So the outcomes, and multiply that by, divide that by how many outcomes there are, which is 6. And when I go through and I calculate this, I should get 3.5. So 1 plus 2 plus 3 plus 4 plus 5 plus 6 divided by 6 is 3.5. So how much would I have to charge per roll to make it a fair game? So therefore, you would have to charge $3.50 per roll, because the amount that you're paying should equal the amount that you're expected to win. You're not always going to win that, but on average you will, or over time you will. So if you think of like that law of large numbers, the more and more you play, overall you should average out and break even. In our last example, we're going to look at a non-uniform distribution. But before we look at our last example, today's code word is Yeti. Again, today's code word is Yeti. So this example of a non-uniform distribution is going to kind of be a lead up into our next lessons, where we're looking at different scenarios or different probability scenarios where it's not a uniform distribution. So in Plinko, the player will drop a coin in the middle slot. So in this case, we're going to say it's going to be dropped here. We're going to drop a coin down here. There are 4 different outcomes at the bottom: 0, 1, 2, and 4. What is the expected value of your drop? So in order to find our expected value we know has the formula, the sum of each outcome multiplied by the probability of each outcome. We know for each outcome we have 0, 1, 2, and 4, but we don't know the probabilities right now. We don't know the probabilities of each one. I do, however, know, or I should remember, how to find the probability. From the Plinko board, we're going to go back to our previous lessons on Pascal's triangle Basically, we overlay Pascal's triangle onto this board to help us calculate the number of pathways. So 1 and 1, 1, 2 and 1, 1, 3, 3, 1, and so on. And we would continue this down until we found out the numbers on each one at the end. And then we would use that to find out the probability. Now, I'm not going to make you go through and use Pascal's triangle to figure out the number of pathways. I'm expecting that you already do know how to do that, so we can move right on past that to kind of save some time. So, in the end, we see at the very bottom, we see the number of different pathways we could land up in each kind of container or slot at the bottom. And if we go through and we add all those up, we should find that there are 4,000 ways. There are 4,000 ways we can get to the bottom. And we're going to use that to figure out our probability. So the probability of landing in 0. Well, in this case, if I look at which containers have 0, 792, 792. So I'm going to add both of those up and divide by the total number of ways, which is 4,000. So 1584 divided by 4,000 is 39.6%. To land in a 1, or to get a value of 1, 494 plus 494 divided by 4,000. This equals 988 divided by 4,000, or 24.7%. For 2, here we have 3 slots or containers that we could land in. 208 plus 924 plus 208, all divided by 4,000. Again, the total number of ways, so just our standard probability, NA over NS, that we've done in the past. 1340 divided by 4,000, 33.5%. And then lastly, column 4, 44 plus 44 for the 2 ways, or the 2 different endpoints, divided by 4,000. 88 divided by 4,000 works out to 2.2%. Now, if we go through, add up all of our probabilities, we should find out hopefully that it equals 100%. In this case, it does. If you're off slightly, then it could just be to a rounding error, or not a rounding error, but you rounded some of your percents, depending on what you rounded them to. So it's okay if you're off a little bit, just keep that in mind. Next, in order to find, again, the expected outcome is equal to the sum of each outcome multiplied by its probability. So that's what we're going to do in the third column. So in this case then, 0 multiplied by the probability as a decimal gives us 0. 1 times 0.247 equals 0.247. 2 multiplied by 0.335 equals 0.67. And 4 multiplied by 0.044, sorry, not 44, 0.022 equals 0.088. And if I go through, add up all of these different values, I should get an expected value of 1.005. So that means the expected value of each drop down the middle is 1.005. Now I could use that to say, okay, well, if I have to drop it down the middle, what is my expected value? If that's the game where I'm only dropping it down the middle, what would I want to charge to make it fair, or to make money or lose money? I could also determine as a player which is the better slot or position to drop the coin down to get the best value. So I could go through and do this again by changing the drop position, redrawing out Pascal's triangle, recalculating the number of pathways, and recalculating the probability. So I could do that in each position where I drop the coin from to figure out the expected value, to figure out where I'm best suited to drop the coin. The last part of this lesson is we're going to use a little bit of technology to kind of go over those same kind of things that we've done, creating a probability distribution table and creating a graph of the scenarios. So we're going to be using Google Sheets, and the same steps can be done in Excel, it just might be slightly different. So looking at Google Sheets, I've created my 3 columns, X, PX, and XPX. So these are going to be my 3 columns. So for X, these are my outcomes. So I had 0, 1, 2, and 4. For the probability of X, in this case, there's not an easy way to calculate it because it's different numbers. We're basically just doing kind of rudimentary calculations to calculate the probability. There's not a specific formula. So here you would have to calculate it beforehand and then enter the values in. So 0.396, 0.247, 0.335, and 0.022. Now the nice thing about this is that I can do some calculations in the cell in Google Sheets itself without having to do any on my own. So to find the X times PX, or the outcome times the probability, I can enter a formula. And to enter a formula into any box or any cell in Google Sheets, you're going to hit the equals button, and then you're going to type in or tell the cell or tell Google what you want to do. In this case, I want to take the first box here, multiply it. I just did Shift 8, multiply by the second box, hit enter, and you've calculated it. And you can double check by clicking on the box. You can see the formula that you've entered, and just to double check to make sure you did the right one. Now in some cases it may ask you if you want to autofill, which basically means do you want to use the same formula for the rest of the cells. You can click OK, or if that doesn't come up, this little blue box here, if I click on that and drag it down, you can see the little kind of dotted line, drag it down as far as you want to go, release, it will carry down that formula for you. And we can see that these are the same values that I got when I calculated it by hand. The next thing I want to do is to calculate the sum. So again, I'm going to enter a formula by hitting equals. Here it's already entered it, or it already suggests it for me, but that's because I've already kind of done this as on my own as an example, so it's recognizing that. If not, I can just start typing in sum. SU, okay, it comes up right here. Sum of a series of numbers and or cells. So this is what I want. I'm going to click on it. It enters it, and now I need to highlight what cells or numbers I'm going to add. So I'm going to click on the first one and hold and drag to the last one. So C2 to C5. That's these numbers here. Hit enter, and we have our expected value that we calculated before, and it works out to the same thing. I can do the same thing for the next. If I want to double check the probability, equals sum. Here it's already suggesting that I add the same values based on the last one, so that's helpful that it kind of understands you're using the same kind of formula for the same values, essentially, kind of. Click on that and then hit enter. Works out to 1 or 100%. Perfect. It has everything that I've needed to calculate, and it works based on the calculations that I've made before. So this is my probability distribution table. Essentially, we see it here. The second column was for creating the expected value. I can also use this to help create my chart or my graph. So I'm going to highlight the two columns. Again, we're only concerned about the outcome and the probability. Insert, chart, and here it's already kind of created it for me. Scroll down a bit. So we just want to make sure that we have everything right. Okay, x-axis is the x. So the first one, px is the other one. Good. We can see the probabilities. You can play around with some of the formulas or some of the kind of the format of it. You can change colors and whatnot. You can change the titles if you really need to. So we could change this into, so there may have been some slight delay there, accidentally pausing it. But again, you can edit it, edit the different parts, changing it to points and whatnot. And the nice thing about this is as well, given a scenario, if I come up with a scenario, I can then change the outcomes to make it more of a game. So let's go back to that Plinko board. Say I know the different positions, I know the values that were in each column, 4, 0, 1, and 2. Let's say I want to change it. Let's say I don't want it to be a value of 1, I want to make it $10, $20, and $40. So by changing that, I've now changed the expected value. The probability is not going to change because I'm not changing the probability of landing in those spots. I'm just changing what the outcome is, and I'm putting it more into a dollar amount rather than points. And the nice thing about having these formulas is that it will automatically recalculate it based on the values or the outcomes that I've now given it. So now if I change it to dollar amounts, $0, $10, $20, $40, I've now determined that the expected value of dropping it down the middle is $10. So I'm expecting to win $10 if I drop it down the middle. So it's a nice helpful way of letting you come up with the expected value of any kind of scenario and lets you change it to make it into a game if you need to. So again, the main thing from this lesson is looking at uniform distributions, understanding what that looks like, how we can recognize them, how we can calculate the probability for a probability distribution table, how we can determine the expected value, and then incorporate that into a game-like scenario. As well, hopefully at the end we've recognized or we've learned how to kind of use Google Sheets to help us do these calculations and create these graphs for us.